Good morning, afternoon, or evening, wherever you are. My name is Felienne, and indeed we're going to talk about how to read code today. I'm on Twitter as well, so if you want to say something about my talk, you can check out my Twitter handle. It's conveniently just my first name. So let's talk about how to read code. Before we really dive into that topic, I want to take you through my personal history of how I came to research the topic of reading code. So we have to go back all the way to the year 2013, when, as Michelle said, I started to teach kids in a local high school on Saturday. So this was a programming club for kids that wanted to learn programming. So I was like, sure, children, I can teach you programming. These were like 10, 11, 12-year-olds. So I thought, how hard can it be? They're tiny kids. I know all about programming. So this is going to be easy because, they're kids. However, I didn't really know anything about teaching, which did make it a little bit harder to actually teach. And the interesting thing that happened to me then is sort of subconsciously, I started to think back about how I learned programming when I was a kid. So this is me when I was about 10 years old, learning to program behind my dad's big computer really big at the time, and I was pretty small. So how did I learn programming when I was young? There wasn't a programming teacher. No one was teaching me programming because none of the adults in my life at the time knew programming. So I didn't really go through a programming lesson. What I did have was this book called Making Basic Computer Games. And this book was allegedly teaching you how to program something. But if you would open this book, it didn't have explanations like this is a variable or this is a loop. It was just printed out code. So just lines and lines and lines of code that you had to manually copy into the computer to get anything to run. And as you can probably hear, I am not a native speaker of English. And at the time, I didn't really know that much English. So like half of the words in the programs wouldn't even have meaning to me. I just copied them. And ultimately, of course, I did pick up some of the concepts. So this absence of a teacher isn't something that happens to me as the single programmer in the world that learned programming in this way. Many people, let's say the children of the 80s, learned programming in such a way. And usually if I give this talk in the audience, I see some people nodding. So I'm just assuming some of you are nodding somewhere out there, because this is an experience that many of us share. The lack of programming education when we were young, the lack of knowledgeable adults, and thus a need for learning from books, because this was way before there was YouTube and the internet and all sorts of tutorials and more friendly ways of learning programming. So the fact that we have this sort of shared history of learning to program isn't something that we left in the 90s, that is only there and doesn't still influence today. No, the fact that we have learned programming that way means that we also think that's how kids should learn programming. We have very much internalized this idea of figuring out stuff by yourself is good and fun and is the way to do it. So that vibe, even though it originates from a long time ago, you can still very much see it in programming for kids books that you can buy now, which is what I did. So when I started to teach in the programming club, I bought a few books for kids, and you still see that vibe there, that sort of Felienne learning to programming in the 90s history. Those type of people are now writing books for kids. You can very clearly see that. So let's look at a few examples of that culture of learning to program. The books will be in Dutch, but there's an English translation underneath. So here's one. The best part of programming is finding mistakes. It's kind of special, right? So I love programming. I program nearly every day, but I don't love finding mistakes. Half of the time, I am the person that puts in the mistakes. So I don't love finding mistakes. So it sort of takes a special person to read this, a special kid to read this and go like, oh, this sounds fun, finding mistakes. Here's another one. You will fail often and it will be frustrating. It isn't necessarily untrue, right? Learning something new is hard and will be frustrating. But the fact that we put this in writing in books for children really says something about what we believe that programming is. And these are books marketed as I said, 10, 11-year-olds. if you have a book about, I don't know, horseback riding or soccer or something, it will not say learning to play soccer is really hard and frustrating, right? It will say, oh, with a bit of practice, you can totally get there. So the fact that we celebrate how hard it is, it says something about what we believe, and it also sort of controls, or at least influences, what type of kids actually think, oh, that sounds fun, something that is hard and frustrating. And here's another one. Never be afraid to mess around and experiment. So this is very much this culture of someone that has learned alone, or maybe in a small group, figuring out stuff by themselves. And they think that that is the only or the best way to learn, is to just figure out stuff by yourself, which is hard and frustrating. So this is the mindset that I had then, right? Now I'm reflecting. But then in 2013, I hadn't reflected on much of this so explicitly. So I assumed that this is how kids would also learn. So I bought these books, I gave the kids the books, and I was like, well, good morning, children. I turned on the computers. There are books that you can use, and you can copy the codes from the books like I did in the good old days. If you have a question, let me know. I'll be sitting in the back, drinking coffee, feeling really good about my service to society, helping the children learn to program. Let me know if there are any issues. Unsurprisingly, people that actually know something about teaching, which was not me at the time, it didn't really work so well. The kids were really like, this is super hard. And especially, I realized that they weren't really learning something. So I would explain something to them in 1 week, and they were making a game, and they're like, hey, teacher, how do I increase the score? So I was like, sure, you do this, click, 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 click. This is what you do. And then the kid's like, oh, that makes sense. Yes, now it's working. And then the next week, they'll be like, hey, teacher, how do you increase the score? It's like, well, I explained this to you 7 days ago. How do you not remember this? So at one point, I also got a little bit sort of frustrated with the potential I was seeing. These were smart kids, right? They were voluntarily coming to the community center on the free Saturday to learn. So it isn't like they weren't motivated. And I could see from my interactions with them that they were like smart and into programming. So if they weren't learning, it was probably me. And as I said, I really didn't know anything about teaching. But at that point, I got really, really motivated to gain a deeper understanding of how people learn basically anything, but especially programming. And what I started to do then is I started to dive into not so much what we know about learning to program, because there isn't so much about that, but I started to learn about how people learn other things, like learning to read specifically, learning to process natural language, because there's so much known to mankind about how people learn their first language, both spoken and written. I was like, oh, this is like a treasure trove of research that I want to dive into. So from looking at what we know about learning languages, I figured out many things about how to learn code, and specifically how to read code, because we never really teach reading code, right? Whether you learn programming by yourself, as I did, or in a boot camp or in a university course, there isn't a university course how to read code. We have programming 1 to 7 or something in the university where I teach, but we have nothing called reading code. It's sort of assumed that if you can write codes, it must mean that you can also read code. But we never teach it. And this was very visible to me in the club as well. So I had kids who were programming in Scratch, which is this visual block language. And then there was this kid in my class, like he made this a week ago, and he opens his program back up. He's like, I don't really remember what this does. So he'd be like, hey, teacher, what does this do again? And I would be like, well, what do you think it does? Because, never be afraid to mess around and experiment. I was very reluctant in giving information. I didn't want to spoil the fun. I thought this frustration that he was feeling was good and was part of learning. So I really didn't want to give the answer. And this is a pattern I still very much see, not just in people that teach children, but also in people that supervise or onboard junior developers. That the junior developer is confused about something and asks a question, and it might be a very precise question. And then we all have this reluctance to give the answer. We want people to figure out this answer by themselves. And this is this, as I said, this culture that we don't really talk about, but that is very much there. The culture of never be afraid to mess around and experiment. So the kid, of course, is not happy, right? He's like, I don't know what this does. This is why I'm asking you, teacher. I am stuck. I am asking for help. And if you compare that to how we teach languages, like imagine you're caring for a 5 or 6-year-old who's learning to read. This kid sees the word apple somewhere. It's like, what does that say, mommy? You're not going to say, what do you think it says? Because it's not helpful for a kid that can't learn or can't read, right? That's still learning. You pick apart the issue. You maybe say, hey, do you know that first letter? It's like the first letter of the alphabet where you recognize it. And if they don't, you'll just tell them it says apple. See the A, B. So you help people typically. We don't expect kids to guess the alphabet, to learn the alphabet by messing around and experimenting. Right? We just tell them what the letters are and they practice a lot. And this isn't just the difference, as you might think, between teaching in school, which is where language is often taught, and teaching outside of school in clubs. Because also in clubs, think about music lessons or sports lessons. We don't require kids to figure out the guitar, right? Imagine you bring your child to a guitar teacher and the guitar teacher says, here's a guitar. Welcome to guitar lessons. You just figure it out. Just figure out what sounds nice. Right? You expect them to practice. You expect them to get little nuggets of information. So both in school and out of school teaching, we expect teachers to break problems down and to guide children or also adult learners into small practice before they can do anything. With code reading, apparently, as a field, as a community, we don't do that. We just say, here's programming code, write it. And that means you can also read it. So we don't teach reading code as a skill. What we also don't do, and now we're stepping away a little bit from children and then really moving on to professional practitioners. We don't practice reading code, which is surprising given the fact that we know from research that people spend about 60% of their time reading code rather than writing code. So most of the time, if you're a programmer, you are reading code more often than you're writing code. However, as a culture, what do we celebrate? What do we all say that is going to make you a better programmer? More programming, right? We assume that if you want to advance, if you want to become a better programmer, you have to do more programming. And we say these things like, oh, you should have a pet project, you should commit to open source code, you should help. It's all about writing. We assume that if you want to get better at programming, you have to do more programming. Of course, this is also this never be afraid to mess around and experiment vibe. And you see this everywhere. Like the days, at least where I am, the days are getting shorter. So it's going towards December, where you have this lovely idea, the advent of code. But the advent of code, where every day between the early December and Christmas, every day you do a little programming puzzle, but you're writing code. We really have this idea of if you want to get better at programming, you have to do more programming. What I also figured out is that we don't really have theories for reading code. Like what happens in your brain if you read code? Luckily, there are some fantastic researchers that are trying to gain an understanding of how to read code. People are using eye trackers, for example, or people are even putting programmers into an MRI scanner to see what happens in their brain. But we don't really know that much about what happens in your brain when you read code. But the good news is we have a pretty thorough understanding of what happens in your brain when you read anything else, when you process information. So I figured out that much that we know about how people process any sort of information can also be applied to programming. And that's sort of what the rest of my talk will be about. So in the rest of the talk, I'll take you through sort of some basic cognitive science about what happens in your brain if you process information. And then afterwards, we'll tie that back into what that means for our programming profession. So the basics first. If information comes into your brain, so at this point, this is probably my voice and my slides through your eyes. If information comes into your brain, it's first stored in the short-term memory, which is a little bit like a buffer in your brain that holds information. And we've known about the short-term memory for a very long time, since the 1950s. A researcher called George Miller was very much a pioneer in this field. And already in the 1950s, he realized that the short-term memory is very, very small. So small that it can only hold between 5 and 9 elements. Not more than 5 to 9 things can be in your brain at the same time. And more recent research even suggests it might be even smaller. It might be like 5 or 6 things. So it's like, how do we do things? To give you a sense of how bad your short-term memory is, we'll do a little memory exercise. So what we'll do is I'll show you a sentence very briefly for like half a second, and you have to try to remember this sentence. So I hope you all are participating in the stream. And of course, no screenshotting, no using your phone. It really has to be your own human memory and not your computer memory that does the memorization here. I hope you're ready. Here we go. So that's like super hard, right? But that's because your short-term memory is so bad. It didn't pick up on all the things. But of course, maybe you're like, yeah, yelling at your computer. Yeah, you're cheating. This is unfair because that was not a sentence. That wasn't even letters. You might be right. So I only like showed you half of the picture. Let's dive a little bit deeper into actually what happens in your brain. So if information comes into your short-term memory, it doesn't stop there. From your short-term memory, the information is sent to your working memory. In your working memory, you could see this a little bit like a processor in a computer that's actually doing something, processing the information. And the working memory doesn't work alone. It doesn't only connect with the short-term memory, it also connects with the long-term memory. So whenever information is sent to your working memory will ask your long-term memory, hey, long-term memory, have you seen this stuff before? So you can see it like this little angel on your shoulder, which is going to say, oh, I know this, I recognize this. So if relevant information is stored in your long-term memory, it will also be sent to your working memory and ease process. So we'll do another exercise, the exact same type of exercise where you see a sentence very briefly. But now you'll see that your long-term memory will be jumping on your shoulder with useful information. Here we go. So that was easier, right? It was still hard. I guess it's still very challenging to figure out the whole sentence, but something was happening, right? Well, in your brain. But I will visualize this as your little friend on your shoulder. She's like, oh, these are letters. Oh, this is an A, this is an M, this is a K. You are recognizing something. So rather than just getting information beamed into your brain, you're like, what? You get a sense of what's going on. So we'll do one more exercise, the exact same type of exercise, and you will see how strong of an aid your long-term memory is in processing information. Here we go. Don't blink or you might miss the final one. So this was doable. I'm guessing most of you have remembered that that was Cat loves cake. And this sentence was equally long as the first two sentences. But now your long-term memory was like, don't worry, friends, I got this. This is a cat, meow. This is loves, loves. This is cake. Mm. Immediately, those concepts are thrown at you from your long-term memory. So you see from this, the more you know, the more you can remember. It's very much like what you already know in your long-term memory makes you see the world in a different way, right? Those three sentences are exactly the same. They're equally long. They have the same number of distinct characters. So that third sentence is only easy for you. It's not really easy. It's not inherently easier. It's just because you've been exposed to the alphabet and to short words like this so often that it doesn't take your brain any processing power because the letters and the words are in your long-term memory. Okay, so that concludes the tiny introduction into cognitive science. Now let's look at how we can use this understanding to look at code. Because if you look at code and you're like, I'm confused, this code is hard, there might be different things that are hard. Those three memory systems each create their own issues in code. For example, here's a program in a programming language called APL, a programming language. So looking at this program, you don't know what it does, I'm assuming. Most people in 2021 aren't so well versed in APL. So I'm assuming you don't know what this is. But why? Why is this program hard? It's because you don't know what the T is. Well, it's not a T, but for now, let's assume it's a T. You don't know what it is, right? So this is a long-term memory issue that you're having. It isn't like that you couldn't remember this code. If I cover it now, it's really easy for you to say do TN. It's not hard to remember. It's not hard to process. You just lack information. Your long-term memory is like, hey, what is this thing? I also don't know. The end. Different code can be really confusing in different ways. So here's another example. This is a little bit of Python that I'm guessing most of you are a bit more familiar with than APL. So this can be hard on your short-term memory, right? Remember, 5 to 9 elements. If you have to remember all of this, customer names, C, first name, for C in customers, it's many things. It can overflow the capacity of your short-term memory because there are too many elements to remember. And here, it very much depends on your Python knowledge, whether or not this is easy, and also a little bit on domain knowledge, right? I'm assuming you all know what a first name is and what an age is and an age limit. If you don't understand the domain, it gets a lot harder to process this. If you don't know Python and you don't know that this is actually something called a list comprehension in which you can create a list based on another list, for you, this might be the first sentence, right? The blah, blah, blah sentence. But if you're very well versed in Python, for you, this might be cat, loves, cake because you've seen such a construction very often. So this code could overflow your short-term memory depending on your prior knowledge. And I'll do one more code example. Here's a little code snippet in BASIC. Probably for this code snippet, your long-term memory is okay, right? Most of this code, you know what let is, and you know what a for loop is, you know what a print is and a return. So I'm assuming the building blocks are okay. Your long-term memory friend will be like, oh, don't worry, an assignment, a string coercion, right? So this is all fine. But then what does this actually do? All the pieces are okay, but what happens here? That's really hard. You probably have to like trace this code. It's like compiling it mentally. You go like, okay, I don't know. Let's take n is 7. What happens then? Okay, if n is 7, then n2 is, okay, this is n1 divided by 2. This is 3. Okay, this is string 1. You have to like step by step figure out what this code is doing. So this is a working memory issue. It isn't like you don't know what's happening, like you don't have the long-term memory. It's like you still are figuring out the parts of the puzzle. So you see these 3 different programs, each really sort of cause pain in a different type of memory, a different memory system. And what I've found that lacking such an understanding of reading code, people just go like, reading code is hard. It's so confusing. It's easier if I just rewrite this stuff myself, which is such a like waste of effort and time because you don't know how to read code. You're just like, well, writing is easier. And I'm like, but this is because you've practiced writing code for 20 years and you never practice reading code. So of course, writing code is easier, right? I'm a long distance runner. It's not very hard for me to run 20 kilometers. But if I have to play tennis, it will be really hard because I hardly ever in my life have done this. It isn't that writing code is so much easier than reading code. It is just a matter of practice. So you can get better at reading code. That's sort of the happy news I'm here to share. You can get better at writing code. One of the things you can realize, that you can remember, is that these different forms of confusion have different solutions. So I hope next time, if you're confused about code, you're not like, this is terrible, but you're like, okay, this is hard. Why is this hard? If you're in this situation where you're confronted with code in which there are either programming concepts or domain concepts that are just unknown to you, you don't have to struggle. You could just practice the things you have to learn. So one fantastic way of practicing is called flashcards. People do this also often when learning a second natural language. So you imagine you're learning French, you put an English word on one side and a French word on the other side, and then you just stack your deck of cards and you pick a random card, or you're like, oh, bonjour. Oh, I know this one. This is hello. You flip the card and you see if you're correct. You can do that with programming syntax as well. Imagine you want to learn APL. It's pretty cool. You can say, okay, on one side of the card, I put the T, and on the other side, I put this actually what it means, that it means encode. You can have a little code snippet to it as well. If you already know Java and you want to learn Python, for example, you could put Java on one side and Python on the other side to strengthen your vocabulary. And the same is true for domain concepts. You could put domain concepts on one side and then the explanation of the domain concept on the other side. If you're confronted with code in which, let's say, half or 25% of the terms are unknown to you, stop. It will not make sense to you soon. It is like trying to memorize this language that I invented specifically for this talk. It doesn't make sense to continue. You will not succeed. You first have to build your vocabulary of stuff that's in the code. And this is like against what we believe, right? Against what we celebrate and say as a culture. Because, oh, you could just Google syntax. Oh, you can just look up syntax. Yes, you can just look up syntax, but it is not efficient. If I want to translate Korean, of which I have zero knowledge, yes, I can Google for words. It will take me forever, and it will take me forever. I will never get better by just Googling shit. It will never work. So if you are confronted with very unfamiliar terms, just try to practice them and build a vocabulary of the stuff you need to know. This code, on the other hand, is confusing in a very different way. Imagine you are a Java programmer. So you have an understanding of what a for is and what an if is and what a greater than is. You understand the basic building blocks. So you sort of succeeded level 1, check. Okay, I know the building blocks. But maybe if you're not so familiar with a list comprehension, it might be easier for you to rewrite this code, because this code, this first code snippet, is exactly equivalent to this second code snippet. This is the same thing. So in the same thing, it's more explicit what happens. First, I'm initializing an empty list. Then I'm looping over the list customers. I'm checking every C in the list. And if the age is bigger than 50, then I'm adding the name of that C thing, that customer, to the list of customer names. So I'm making a list of all customers that are over 50. If the second form is easier for you, there's no shame in that. It's totally fine to massage code a little bit so that it is more closer to your long-term memory. So this transformation makes it easier for you because in the second form, you have less chunks. You divide it into pieces of knowledge called chunks that you already know really well. I talk about this in my book as well. This is something I call a cognitive refactoring. So it is a refactoring in the sense that the external behavior of the code stays the same. However, typically we wouldn't see this as a refactoring because there is always this assumption with a refactoring that it's supposed to make the code better, more maintainable, easier sort of for everyone, and not easier for you for this point in time. So a more logical refactoring would be the other way around, right? And some people might now also be yelling at their screen, being like, no, you're making the code worse. But the goal isn't necessarily here maintainability in the long run. The goal of such a cognitive refactoring is understandability for me now. And I might later like re-roll this or just like delete my commits and leave the code base as it is. I give much more examples also of my book of cognitive refactorings. Another one is to inline a method. So if you're unfamiliar to a code base and the code is really nice and well structured in different small classes and methods, this is what we want. But then reading the code for me as a newcomer in this code base means, oh, this is a method. Where is this method? Control F or like control click. I have to hop to that method. It gives me all sorts of extra like energy in my brain. And then I have to read the method there. Oh, it connects to that method. I have to go there. So my energy now is spent on navigating the code base. This is energy I cannot spend on understanding. So just inlining a bunch of methods and then reading top to bottom to gain an understanding of what is happening can be very valuable. And that is mostly definitely not seen as something that is a proper refactoring, because you're making the code less maintainable. But there's really this difference between understandable now and maintainable in the long run. Then let's go to this final type of confusion. This is also confusion, of course, that happens commonly, where you have a piece of code and your working memory is like, oh my God, my processor is getting overloaded from all the steps I have to do. There's many things also you can do. We have much examples in the book as well. One thing that you can do is to try to make a little state table. So you try to understand what is the value of each variable in each step of the computation. So you can say, well, first in the initialization phase, before we go into the loop, these are the values that the variables have. And then in the next step, these are the values that variables have. And this way you can try to gain an understanding of what is the relationship between variables and values. And you could do this manually, but of course you could also do this partly aided by a debugger that could tell you the values of different variables. So if your working memory is overloaded, then you really have to offload some of your processing power out of your brain, because your processing power in your brain is very limited. So you either want to do this on paper or in the IDE, or maybe as a group collaboratively together. You can also share different information, but that's what you do if your working memory is overloaded. So these different types of confusion, different types of code give you different types of confusion that each have a different solution. So I hope, just to wrap it up, because we're nearing the end of this talk, that by understanding your own understanding and also your own misunderstanding, you can become a better programmer, because you're better like prepared for these different types of confusion. And you have like this little library of solutions, like, oh, my working memory is overloaded. Let's draw something. Oh, my long-term memory seems a bit outdated. Oh, let's do some flashcards and let's expand the vocabulary of stuff I know, which hopefully will help you to be less scared of reading code and more prepared. If you want to know more, I mentioned it a bunch of times. Michelle also mentioned it in the intro. You can read my book called The Programmer's Brain. It's out at Manning. I'm sure the people at YOW can put a link to the book somewhere. I have a link also at the end of my talk in my slides if you want to check it out. So reading my book is definitely something you can do that helps you. We sort of covered chapter 1 and chapter 8 in this talk. So I explained these three memory systems, and then in different types of, in different chapters of the book, I talk about the effect on refactoring and variable names and design patterns. All these things we know from programming sort of that are hard. I contextualize them with understanding from cognitive science. What you can also do, which I've come to do for a year and a half now, basically since the pandemic started, is you can start a code reading club at work. This is something, I have a link also to some resources at the end of my talk. This is something that you can do as a group. So what a code reading club is you come together with a bunch of colleagues, you take a piece of code, can be from your own code base or grabbed randomly from GitHub, doesn't really matter, and you just read it together. And then we have some exercises that I will link to at the end of the talk. Exercises like, let's summarize this code. So everyone summarizes the code and you compare notes. Let's decide what are the most important lines of this code. And then you discuss that, which is a really nice way to get to know your colleagues and how they think about code, but also a really nice way to practice code reading. And it's really nice that after I started this idea, many companies around the world are trying to do 2-week or every 3-week code reading club. And they really say that they are benefiting from practicing this skill deliberately with a small group of people. So that's also definitely something you can do. If you want to get better at code reading, you just have to do more code reading. It will help if you do it at least in a deliberate way with specific exercise. So that's everything I wanted to share. I know you already have seen many talks today, so I'll do like a very brief summary of my talk before we open the floor for Q&A. So what did we talk about today? We talked about how to read code, which can be challenging because as a culture, we very much embrace interacting with code as a way to advance our skill. Never be afraid to mess around and experiment. However, we know from cognitive science that if you process information, your short-term memory and long-term memory and working memory really work together. So just writing lots of code isn't necessarily going to help you read code. What you could better do is to understand these memory systems and to use the right solutions for the right problem. For example, practicing syntax, refactoring code to help your own long-term memory, and support your working memory if you feel that it is outdated or overloaded. That's it. If you want to know more, as I said, I'm on Twitter. My Twitter handle is @Felienne and my website is felienne.com. If you want to know more about the book or buy the book, I'd be very grateful. You can go to felienne.com/book. If you want to know more about code reading clubs, you could go to felienne.com/club, where we have a website with free and open source resources to get started with your own code reading club. We have like your first meeting agenda, pick this exercises, pick this code snippet, the second one and the third one to help people get started. And what we also do together with some other people in the code reading club community, we have a monthly open code reading club online meeting. So if you just want to join us, get the sense of what a code reading club is before you start one, we have an agenda also on the website with the next code reading club. It's the first Tuesday of every month. Maybe you're wondering, before we go to Q&A, tiny story. Maybe you're wondering about the children, like, hey, Felienne, this story started with you were failing at teaching children, and then you wrote a book. Well, that's all fun for you, but what happened to the kids? So that's a great question. Basically, two things came out of this exploration into what is programming do to your brain. One was the book, and the other thing that came out of this was a programming language for kids. So in the same vein as the type of things I talk about in the book, I made a programming language for children called Hedy, free and open source, by the way, that tries to also separate the long-term memory and the short-term memory and the working memory better. So I could give a whole talk, but we don't have the time. But if you want to know more, you can go to felienne.com/Hedy to check out the programming language. If you are teaching children, as I said, it is free and open source. So if you want to check it out, I'll be very honored if you would give it a try. Then this was mentioned by Michelle as well. I am one of the hosts of the Software Engineering Radio podcast. So if you want to listen to me for many hours more, this is possible on Spotify and iTunes. Software Engineering Radio is a weekly interview-based podcast where we interview people from software engineering community, both on technical things like Docker containers or Kubernetes, but also social skills like how do you do an interview, how do you onboard people. So it's really the whole broadness of software engineering. And with that, I think we can go to Q&A.
Fantastic. Thank you so much, Felienne. I got to the end bit. Won't someone think of the children? Okay, so the first question is from me, but other people did vote for it. So I was wondering if you ever find different people cognitively refactoring the same pieces of code over and over due to each person's different understanding. And does that affect a team where it's kind of like, people changing it this way and then that way, because it doesn't make sense to me, it doesn't make sense to you, that kind of thing?
Yeah, this is very true. So it's not necessary that, first let me clarify, it's not necessary that such a cognitive refactory actually ends up in your code base. This could be very well something you do locally for your understanding. But the pattern that you described does happen, where this could be tiny things. Like I have one programmer in my team and he puts a space between the function name and the first bracket, which I just hate. So if I see it, I undo all the spaces. So you can have this like mini turf wars, and it can be about other things as well, using a list comprehension or nulls, using lots of static classes and static methods, like a utility clause where everything lives, where some people might say, no, this really belongs with this class thematically better. And then someone else might move it back. So yeah, that's really annoying. This is, by the way, something, if you would do a code reading club, that's the type of things you would then discuss in a separate, then you're discussing a piece of code that isn't your code necessarily. So you can have these discussions without talking about your actual code base and maybe make a joint decision there. This is something that could help, but yeah, people always have personal preferences. And one of my good friends, Peter Hilton, he always says you can write Java in any language, which I think is true. So it's not just what people like, but it's also the background that they come from. So I came from C# into Python, and I'm sure my first few years of Python were very C#y, right? Something like list comprehensions, that's really very Pythonic. It just takes a while to think of that as the first, your first choice. And very often still, if I do a for loop, I will type for each. And I'm like, you know, go away, Angel. This is not C#. So your first program or your first programming languages will definitely stick with you, and you will see that in your idiom. You'll have something like an accent in code, and it can be annoying if that happens. If different people with different accents keep changing the code in different ways. Yeah, for sure.
So Ashley says, did you draw your own slides? Very engaging.
Yes, I actually have an extra slide for that question. Sometimes people ask me, how did you make your slides? Yes, I make them by hand, but not by hand. I have an iPad with an iPad pencil, and I use an app called GoodNotes. They don't pay me to say this, but this is what I use. And it's really nice because it allows you to make this little library of your own like clip art. So you draw all these images once, and then now if I need to have like kids, I can just look in my own library for like laptop, kids, all these things. So that really makes it easy to design your slides this way. So great question, Ashley. Yes, I did draw that by hand.
So what's it called? GoodNotes.
GoodNotes, yes.
Okay, cool. Next question is from Richard, who says, are there one or two techniques which you have seen be the most successful with the most people?
Oh, that's a great question. So I think cognitive refactoring is something that people do intuitively. This isn't something like I invented. I gave a name to it, so this might make it easier to talk about it. But I've seen many people do this, where they massage the code a little bit in various ways. It is something that just makes sense. If code is very confusing and all the variable names are X and Y and Z and B12, then you'll probably just start with, okay, what is this thing? Let me give a better variable name as a means of understanding, which also is a cognitive refactoring in a sense. So I think this is something that works for many people because people already do it. But then I think the other thing with the flashcards is also something that just works remarkably well. And that is interesting because it's, as I said, it's so much like goes against the grain of what we say to each other. I have this whole chapter in my book about how ineffective it is to look up stuff on the internet. So this, oh, you can just Google the syntax. It is a lie. Of course, yes, you can Google the syntax, but like I want to like read my entire chapter to all of you right now, but you can buy my book and read it yourself. It takes you like 15 minutes to get back from such an interruption because you go on Stack Overflow and it has all these nice little banners. Or it's like, oh no, this is not the right page. Oh no, this is not the right page. And then someone has like a mean comment on Stack Overflow. Oh, why are people so mean? It takes so much energy to go out of your code base and to go back in. And also you're giving your brain the signal like, oh, I don't need to remember this because I can just look it up. So if you want to, if it's like this one life hack that really works, there's a secret trick that actually helps you learn a new programming language. It is really boring and it's not a thing we do. But if you already know one programming language, really, you take these cards and on one side you put, on one side you put C# and on the other side you put Python and you put them in your pocket. And every time you're in the train, you just try to like memorize the syntax and see if you got it right. It is a very good way to learn both programming syntax, but also, as I said, domain concepts. If you're new to a domain and all the domain concepts are very overwhelming, all the domain concepts on one side and the definitions on the other side. And you can do it on paper, which I like, but also there are many apps that you can use. We have a few examples in the book as well. You can just download an app, and there are apps like Anki app. They already have Python decks, so you don't even have to make them. You can just take the decks that exist. This is something we just know from cognitive science, that this is called retrieval practice, like you're trying to remember. It's just a great way to strengthen your long-term memory. It's not like free, it takes your energy, but it works remarkably well.
Nice. Did anything really surprise you when you were researching this kind of stuff for the book about weird ways that programmers' brains or anybody's brains work?
Yeah, so I do think I was surprised by this long-term memory effect, right? That this realization that, as you saw with the 3 sentences, that the way I look at code, because I'm an expert programmer, I'm not just an expert programmer. Also, if I look at my own code base, everything makes lots of sense to me because it's designed the way I think it should be designed. That if I'm onboarding an undergrad, for example, that will do a little project with me, which happens like every 6 months. What I see and what they see isn't the same, right? It is very much, for me, it says cat loves cake. And for them, it's like, this is hieroglyphs. So the fact that what you already know so much impacts what you see, and thus what you can remember and what you can process, that's really been eye-opening to me, because I will admit on camera that sometimes I've onboarded students and I explain all the code to them, and then the next week they don't know anything, or I tell them, okay, so I give you this, I gave you a 5-minute explanation of the entire code base. Now you can close this issue, don't you think? And the students, of course, sure, professor, I will do this. And then they don't, and then 3 weeks later they come back and they haven't done anything. And I'll be like, oh my God, oh, children these days. When I was 20, right? We've all had these thoughts. I hope that I'm not very weird and mean that way. So that is very much something that has changed. I have a chapter also in my book about how to onboard people. And a good way, a not good way to onboard people is to give them a 5-minute explanation and then have them fix an issue or implement a feature. You have to really take it slow. So I think that for me was the biggest eye-opener, that it doesn't matter if you're like super smart and you have lots of experience coming into a new programming language and or a new code base with a new domain. You will be a baby again, and you'll be like, oh my God, I'm learning Rust now. And now I'm again like, oh my God, this is so hard. So it's good also to keep learning, because then as someone that's more senior, you keep feeling this pain of how hard it is to learn new things, which is good, because then you might be softer on people that you're onboarding.
Mm. And finally, what resources or books, apart from yours, of course, do you recommend to deep dive into some fundamental cognitive science concepts?
Oh, that's a great question. So I'll just grab my book because I have it. Because in the final pages of my book, I actually make some recommendations that I then forgot. So I can look them up now.
Okay, everybody start taking notes, pens, ready.
Yes.
The professor is in the house.
Yes. So there's one book that I really very much like, and it's called How the Brain Learns Mathematics. It's a nice contrast with learning language, and it very much explains how people get a sense for numbers. And getting a sense for numbers is very close, I think, to getting a sense for programming. I also very much like The Philosophy of Software Design by John Ousterhout. It's also a very nice book from a distance that sort of tries to do it a little bit the same, I think, as my book does for cognitive science, but then he does it for philosophy. So it also talks about stuff like, what's the stuff we value and why do we value that? So that's really nice. And also one more suggestion that I really like. It's a tiny book. It's physically very like a pocket book. And it's called Software Design Decoded by André van der Hoek and Marian Pieter. And this book has 66, I think, ways in which things that you can do if you want to design software. Very simple things like draw a diagram, map out your story. So that is also something I really like, because as also my book is trying to do, it sort of gives you this vocabulary. It gives you this little toolkit of, oh, I'm stuck. Well, I can take one of the 66 ways in which people design software. So those are my recommendations I would give that I put in my book. So they were the best ones.
Fantastic. And now I know I said that was the last one, but another one has cropped up. Hooray for online things. So this one's from Kevin. How long have you implemented these strategies with your students/mentees? And are there other things that you wish to try?
Oh, that's great. So yeah, it's been really a steep learning curve for me. So I guess sort of 2016, 2017, when I started to figure out how to do this. So already, as I said, 13, 14, when I started the programming club, I already started to make some changes, but then I think 4 or 5 years that I really actively tried to help students do little memory exercises, but both with kids in the high school age as also in university with a little bit older students. So those are all things that just we know they work from cognitive science, and it's just a matter of how exactly to apply them in programming. So sort of a few years, and it seems to be going well. So things I would like to put more attention on, but it is this tension, right, between what people believe will work, also what students or kids will believe works. So students that come in now also have this belief that they should do more programming to learn programming. So doing things that isn't that sometimes also can give tension. And if people are told to do something they want or they don't believe has value, it gets really hard. So interestingly enough, doing this stuff with middle schoolers is easier because they just do what you say. And then with students. So some things that I've also been experimenting with, I gave another talk about this a while back, is actually read code aloud is a very strong memory aid. We haven't talked about that in this talk, but if kids learn mathematics, right? How the brain learns mathematics, like tables of multiplication, you don't learn them silently. You do like 2 times 3 is 6, 3 times 3 is 9, many times. So vocalization is a really good memory aid. There's also research, I talk about this in my book as well. There's also research that shows that if programmers read very complicated code, they'll have more tongue muscle activity. You can measure this with a sensor on in your jaw. So if we do code processing, the part of our brain that is thinking about reading aloud is active. So reading aloud is a really good strategy, and something that sort of we already have as a culture is this thing called rubber duck debugging, right? That once you start explaining something, once you start vocalizing something, that helps even if no one is there to listen and it's just literally your rubber duck. So that's definitely something that is very valuable, but it's sort of hard to do also in an open office plan setting. You might not want to talk to yourself. It's a bit weird and people might overhear you. But that's definitely something that I want to explore in a little bit more depth, because we just, as I said, from research, we know that saying stuff aloud, like I used to be in Catholic school when I was a kid and we had to say like prayers in the morning. You could wake me up at night and I could still do the stupid prayers because you've chanted them so often. It's just a really good memory aid. So some exploration into vocalization and code and how you would do that is definitely something I want to pursue a bit further.